Welcome. So, for this lesson, we're going to talk about natural disruptions to ecosystems. And natural disruptions to ecosystems, just like those that are man made, can have environmental consequences. And part of environmental science is not only studying how we affect ecosystems and how we affect organisms in their environments, it's also studying how natural processes do so. So, let's get into some more detail. Before we can move on, we need to distinguish between those processes that are natural, that occur without human interference, and those that are anthropogenic, which are caused by humans. So in this case, we're going to define a disturbance as any event that's going to disrupt some facet of an ecosystem, a community, or a population. And in that, it's going to likely affect the availability of resources, or in fact, the physical environment, or things like abiotic factors such as climate as well. So, some examples of natural disturbances are wildfires, fires, insect outbreaks, epidemics of disease, droughts, floods, hurricanes, windstorms, landslides, avalanches, volcanic eruptions, and there are a few other examples we're going to talk about in a moment. Some anthropogenic examples are deforestation or logging, urbanization, climate change, and pollution. And just a friendly reminder, whether or not you've encountered this in the notes or not, anthropo literally means human, and genic means caused by. This is an extremely important vocabulary term, anthropogenic, because we want to distinguish between the things that are caused by humans, which are anthropogenic, and the things that are natural that would exist without humans interfering with the environment. So notice each of these things that are listed under anthropogenic disturbances are things that would not exist without humans being here. And part of the reason why we want to make this distinction is because we cannot necessarily affect these natural disturbances. For example, we can't stop a hurricane in its tracks. We can't, in most cases, predict or prevent volcanic eruptions. However, we can try to lessen the impacts of things like deforestation or urbanization, because since they are caused by humans, they can be lessened by humans. And then just to point out, natural disruptions have happened throughout the history of life, throughout the history of this planet. They can have consequences just as drastic, if not more severe, than those that are caused by humans. Disruption, change, these are just kind of elements of existence on Earth. So let's talk about some of these processes that can have effects like these natural disturbances. And these happen on a variety of timescales. So, for example, you can have periodic processes. These happen at regular, repeated intervals. So, some examples of this are tides. So, this diagram here is showing the tides in a certain area. In this case, Chesapeake Bay, Virginia. So what you're looking at is you're looking at the sea level, how far the ocean is rising on a beach, and you'll notice it has this very specific pattern going up and down and up and down, and it's a very regular pattern that can be very easily predicted. If you know, or remember anything, if you've had physical science, you'll know that this is dependent on the gravitational pull of the moon, predominantly, but also affected by the gravitational pull of the sun as well. And this is a very regular phenomenon. If you've ever been to the beach, you may have seen tides rising and tides falling if you've been there for a very long period of time. Then there are some other disturbances that occur on a yearly schedule. For example, seasons in and of themselves can be disruptions that occur on a yearly schedule, fall or winter, which will with them bring potentially some of these disturbances. For example, winter can bring ice storms, summer can bring heat waves, and there are also some other seasonal variations like monsoons, which are seasonal rains, which in some areas of the world can bring the entire year's rainfall in just a few short months period of time. And usually in areas with a monsoon, there'll be a monsoon or wet season, and then there will be a dry season. And this is something that you can predict with regularity because it tends to follow a pattern. And then there are some of these periodic processes that happen over a very long span of time. So there are some climate cycles that we'll talk about in a moment. These things span tens of thousands, in some cases hundreds of thousands of years. So, for example, climate cycles, which if you ever do some research on this, are also called Milankovitch cycles after the guy who first proposed them, are determined by a lot of these physical characteristics of the Earth and its orbit around the sun. So, one of these things is the shape of the Earth's orbit. For example, here in this diagram right here, this is the shape of the Earth's orbit, which is also known as eccentricity. Sometimes the Earth has a more oval shaped orbit, and sometimes it has a more circular orbit. This can affect climate because if we have a more circular orbit, then we have pretty much standard, average amounts of solar radiation hitting the Earth. If we have a more oval or elliptical orbit, then there are going to be sometimes when we're farther from the sun and sometimes when we're closer to the sun, which can affect how much solar radiation we're getting, which can therefore affect temperature. Then there is obliquity, which is also called the tilt of the Earth's axis. So right now we're at about 23.5 degrees tilt. That is the tilt between the rotational orbit and kind of our plane of rotation or revolution around the sun. And that affects the climate because it affects seasonal length. So if you have a more extreme tilt, you're going to have more extreme seasons. And if you're confused about this, don't worry. We're going to talk about this more in Unit 4 when we talk about how things like the Earth's tilt affect our seasons and affect incoming solar radiation and therefore average temperature. And then there's also the direction that our rotational axis is pointed. This is called precession. And sometimes it's pointed the direction that we're kind of noting here is towards the North Star versus towards Vega, but this can affect when our northern hemisphere is pointed towards the sun, and therefore is in summer season versus when our northern hemisphere is pointed away from the sun and is therefore in the winter season. So these things, precession, obliquity, and eccentricity, have these characteristic patterns where they will increase and then decrease and increase and then decrease. And then if you look at this bottom graph right here, these are showing the average temperature on the planet, and these are showing advances of glaciers. So everywhere you see this kind of gray bar, those are all ice ages. So based on how our orbit is, whether it's circular or elliptical, what our axial tilt is, and also what direction the Earth's axis is pointed, that will affect how much solar radiation we're getting, and that can cause us to either enter an ice age or that can cause us to enter a warming period. And there are very regular cycles of this that can be seen through evidence that we'll talk about later in this lesson. Then, these are periodic processes. Now we're going to talk about episodic processes. This is maybe a little confusing as it was to me because you may think of episodes of a TV show that release regularly, but unlike periodic processes, episodic processes may occur fairly frequently, but the intervals at which they occur are not really regular. So some of the examples of this are El Nino and La Nina, which we'll talk about in Unit 4. That is an irregular pattern of changes in the climate throughout the world. For example, right now we're in an El Nino year, but other years we're in a La Nina year. And this occurs every 2 to 7 years. And notice it says 2 to 7-ish years because there is not a predictable pattern of this. We're not 100% able to predict when we'll be in an El Nino year versus a La Nina year, which has consequences for the climate around the world. There are other episodic processes like earthquakes or volcanic eruptions. You may have heard that periodically, for example, well, not periodically, episodically, the island, the volcano that makes up the island of Hawaii has had multiple eruptions. One of the peaks, Mauna Loa, has also had frequent eruptions, but they don't follow any predictable pattern. So when you look at this graph, this is showing how long eruptions are lasting. And notice that in different years, you may have frequent eruptions. For example, this period right here in what looks like the 1870s, there was pretty much continuous eruption of Mauna Loa for almost a decade. Whereas there are these longer periods of time here where you may have inactivity and a volcano goes dormant. And we'll talk about dormant versus extinct volcanoes a little more in Unit 4. So these aren't predictable processes, but we know they're going to happen. Until you have some evidence that a volcano has gone extinct, which it takes a while to determine that, um, you can be guaranteed that there might be an eruption somewhere in the future, but we cannot predict when it will happen. And this means that we can't predict when these very devastating, in some cases, disturbances are going to impact local environments and people. So this is a graph showing you the occurrence of the El Nino Southern Oscillation, which is the El Nino and La Nina cycle. It's characterized by differences in sea surface temperature off the west coast of South America, and that's kind of what's represented by this ONI index that you're seeing on the y-axis. But what you can see is whenever this value is above 0, that means you're in an El Nino year. And whenever it's below 0, that's going to be a La Nina year. We will talk in a great deal more detail about this in Unit 4, including some of the effects this has on global climate. But what you can see is there is not a very predictable pattern. For example, in around 1974 and 1976, we had 2 La Ninas in a row without an El Nino in between. And then in 1990, it looks like 92 and 94 maybe, we had 2 El Ninos in a year without having a La Nina in between. So there's not a definitive pattern where we can predict, okay, this is going to be an El Nino year. Only when we take measurements and start to see, oh, the sea surface temperature in this area is higher, then we can start to say, okay, this is probably an El Nino year. Then there are random processes, and these you cannot predict their frequency or their timing because they don't have any particular pattern. So some examples of this are meteor impacts. For example, most of you guys probably know that the meteor that made most of the non-bird dinosaurs go extinct happened about 65 million years ago. You may see some talk in the news about NASA monitoring some asteroids or meteors that look like they're coming close to Earth and worrying about an impact, because what we'll see in a future slide in this lesson is that some of the major differences in climate, major natural disturbances, have been linked to meteor or asteroid impacts. But we can't necessarily predict when they'll come. It depends on a lot of different factors and a lot of different interactions between different bodies in the solar system. So we can say we might have a near miss or we might have an asteroid coming kind of close to us, but it's hard to calculate all the kind of gravitational interactions. Then we have things like lightning strikes. You might be able to say, okay, we're more likely in this part of the year to have lightning strikes because we're more likely to have thunderstorms. But you cannot absolutely predict when and where lightning will strike. So this graph is showing you lightning strikes in the Sierra Nevada mountains, which is in California, not too far from the Rocky Mountains, and it's showing you how many lightning strikes they had per year from 1985 to 2000. Notice there isn't quite a pattern, and also notice even though you can kind of see a little bit of a pattern where it's increasing and then decreasing, this is per year. If we looked by month, we would also see that it's a pretty random occurrence. Sorry, I tried to find graphs of meteor impacts, but that's a lot harder data to find. And a note, you can have some things that are hard to tell whether they're periodic or episodic. For example, when I was going through some of this stuff, I saw questions about whether hurricanes are episodic or periodic. And the reason for that is you may have something like hurricane season, which is periodic. There are specific times of year when we can be fairly certain that hurricanes will develop in the Atlantic Ocean, other times of year when we can be certain that hurricanes will develop in the Pacific Ocean, and we can be fairly sure that at least one of those is going to strike, say, the eastern United States. However, we cannot necessarily predict when individual hurricanes will form. So those, while they occur frequently, we don't have a regular pattern to them. So individual hurricanes are episodic, but hurricane season is periodic. Same thing with something like tornado season. There are certain times of year here in Dallas when thunderstorms are more common, for example, spring. And during those times of year, we know that tornadoes are more likely. Why? Because we're more likely to have thunderstorms. Can we predict exactly when and where a tornado will strike? No. That's why individual tornadoes are episodic because we can't really predict them. They happen with some frequency, but they're not on a regular pattern. Whereas things like tornado season are periodic because you can predict, okay, around this time of year, we're going to have probably some tornadoes in this general area. So Earth's climate has natural variation. It's changed over time. It's not been constant. So some of the factors that affect Earth's climate are the strength of the sun's output. For example, in this graph, what you can see is my apologies. What you can see is that around when the sun formed, it had very low luminosity, meaning that it wasn't putting out as much light and heat as it is now. Now that has been steadily increasing until this point, where around 4.6 billion years after the sun's formation, we're at a certain level of sunlight. And as time goes on, the strength of light that the sun is emitting will increase. And obviously, the more intense sunlight, the higher the temperatures. Changes in the Earth's orbit, as we saw when we were looking at the Milankovitch cycles, the amount of greenhouse gases that are in the air. So this was kind of the best representation I could see. A lot of times, some of the most potent greenhouse gases are going to be the ones that contain carbon. So for example, when we go over climate change, we'll talk about the fact that CO2 and CH4, carbon dioxide and methane, are some of the more potent greenhouse gases. Water vapor is also a potent greenhouse gas, but the amount of water vapor in the atmosphere, that depends on humidity and things like that. However, something like oxygen, nitrogen, ammonia, those aren't going to really be greenhouse gases. What you can see is during certain parts of the Earth's history, for example, here, the Hadean Eon, which was very soon after the Earth formed, there was a lot of ammonia/methane, not so much water vapor, not really very detectable amounts of carbon-containing compounds in the atmosphere, and a bunch of nitrogen. That means that there were some amounts of greenhouse gases like methane, a little bit of the water vapor as well. However, there were other processes that were keeping the climate hot, which we're not going to get into. In the Archean Eon, you can see that there were a lot of carbon-containing compounds, probably carbon dioxide, and there was a lot of water vapor in the atmosphere. So these greenhouse gases trap a lot of heat. So the Archean Eon was probably pretty warm. Whereas in all the eons since then, the Proterozoic, the Paleozoic, the Mesozoic, and the one that we're in right now, the Cenozoic, you don't have quite as much carbon-containing compounds, water vapor as you did in previous eons, so those aren't contributing quite as much to the Earth's temperature as, say, in the Hadean Eon. That being said, we are increasing the amount of carbon dioxide in the atmosphere, which is having an impact on the climate. Ocean currents distribute heat from the equator, where there's the most intense solar radiation, to the poles. We'll talk about this more in Unit 4 when we talk about the ocean. Volcanic eruptions. This can release ash into the air, and that ash can block sunlight. So in periods of time when you had a lot of volcanic activity, you had a lot of this stuff in the air that was blocking sunlight, and that has a cooling effect on the Earth's climate. Changes in vegetation. So if you have some areas where you have a lot of vegetation, those plants can be absorbing solar radiation, which can have impacts on the local climate and the global climate. For example, where you have forests release a lot of water vapor into the air, which can, in some cases, act as a greenhouse gas, and in other cases, can help kind of moderate the temperature to keep it from going too extreme. And then, as we said before, asteroid and meteor impacts can also affect Earth's climate, such as that big asteroid that impacted at the beginning of the Cretaceous period, about 65 million years ago, in the Yucatan Peninsula. So how has Earth's climate varied? So we have been able to kind of estimate the average global temperature, amounts of greenhouse gases in the air, etc., for the past 500 million years or so, and I'll talk about how in a few moments. However, here you see the average global temperature, and in this graph, for example, anything above this line means that during that period of time, it was too hot for polar ice caps to be in existence. Anything below that line, it was cool enough that polar ice caps formed. Polar ice caps can have a very large impact on the climate. We'll talk about that with sea level in a minute. And keep in mind, climate is a pretty complex thing. So we're talking about some general disruptions, some general things that can impact climate, but obviously we're not getting into everything here. So you can see there have been periods of warmer temperature, periods of colder temperature. You may know those periods of colder temperature as ice ages. So how do we know what the climate was like in the past? It's not like we had measuring equipment 400 or 500 million years ago. Well, there's a few things that can be studied. So ocean and lake sediments, coral reefs. This diagram right here is showing the growth of coral because coral adds to its exoskeleton every year. And so when you look at these patterns of the thickness of the coral skeleton, you can actually see seasonal variations, and sometimes you can see yearly variations, which let you know differences in climate. You can also use tree rings to look at that as well, though some coral reefs can have been in existence for over 1 million years. Trees don't tend to live as long, so they're more windows into more recent climate. The way we found out a lot of the very distant past climate has been through ice cores. So what scientists do is they drill into ice, usually in Antarctica or in glaciers, and they drill this core. So they bring out this giant cylinder of ice. And what happens is when you have a glacier or an ice cap, every year snow falls. And then when it doesn't melt in the summer, it builds up. It starts to get compacted by the layers above it, and it forms layers of ice. And then there are seasonal differences in snowfall. You might have less snowfall in the summer, more snowfall in the winter, and you can kind of see these patterns in the ice. Also, since the ice doesn't allow gases to leak out, it traps some of the atmosphere, especially in like little bubbles, in the ice that you can then melt, analyze the gases, and figure out, okay, what was the carbon dioxide concentration like? What was the oxygen concentration like? And so you can take measurements of the amount of greenhouse gases in the air and use that to figure out what the average global temperature was. So sea level has varied for mostly these two major reasons. The changes in the amount of ice that's locked up in glaciers and ice caps. For example, when you have an ice age and a lot of the Earth's surface water has been frozen into glaciers and ice sheets, that's going to cause sea levels to drop because there's less water available to be in the ocean. Then you'll have these shallow coastal areas be kind of exposed to air and they'll become land. So you might have had organisms living in those areas. This is showing a map showing the extent of glacial ice. So ice sheets covered the United States up until it looks like a lot of the Northeast and a lot of the areas around the Great Lakes were just buried in ice. However, there was more land available because it was exposed by a drop in sea levels. When glaciers and ice sheets melt, there's less water locked in ice, and so sea levels will rise. So this line is supposed to be showing over the past 5 million years the highest level that sea levels were. So sometime in the past 5 million years, you'll see here like Florida would have been very tiny because sea levels were higher. Then there's thermal expansion or contraction of water. When you heat water, it expands in volume. So if you have higher temperatures in the ocean, that water is going to expand in volume. And you can't really measure this as easily in, say, a pot of water or a glass of water because it's a small amount of expansion. But when you have a mass of water like the ocean, small differences in temperature can cause these larger changes in the volume. So when the ocean temperature is warmer, it's going to expand, and that's going to raise sea levels. So more land will be underwater. When water temperature is cooler, then you're going to have the ocean water contract. That's going to be a lower volume. Sea levels will drop. But keep in mind, when it's warm, you're not going to have ice sheets, those have melted, and you have this thermal expansion of water. So you're going to have two factors raising the sea level. That's something we're facing in the next 50 or 60 years. When you have the temperatures drop, you're going to lock up more water in ice sheets. That's going to cause sea levels to drop. And then you're going to have thermal contraction of water, which will also cause sea levels to drop. So if we enter another ice age, you'll have both of those factors decreasing the volume of water or in the oceans, and that's going to decrease the sea level. So this is a neat image. It's showing at kind of about 20,000 years ago when we were locked in an ice age. It was a pretty heavy ice age where a large chunk of the northern hemisphere was covered in glaciers and such, what the coastlines looked like. So there are a few things I just wanted to point out. These lighter shaded areas are areas that were land during the last ice age because so much water was locked up in these ice sheets that these kind of shallow coastal regions were not flooded, so they were exposed to land. So we have a couple of regions, Beringia, which is the name, kind of tentative name given to a region between Russia and Alaska that was probably exposed to land, exposed to air. This is likely an area that was solid land that people who eventually came to settle the North America and South America regions were able to use to cross over from Asia, because humans evolved in Africa, then spread to Eurasia, and then from there spread to North and South America. There are some areas right here, for example, in Indonesia, that they're now currently a bunch of little isolated islands, but they were connected by land, and that allowed migration of species as well. Same thing for Australia, as well as parts of Papua New Guinea, which would have allowed migration of animals and humans into these areas much easier. You'll also see, for example, South America had larger land mass. This area in the eastern seaboard, as well as the Gulf of Mexico, we had more land in that area as well. And in fact, cool fact, when sea levels were lower, some of these areas that are now kind of shallow coastal areas where, like 50 meters or less than 100 meters, you'll touch bottom on the ocean, they used to be dry land. So this, for example, map shows the light green shows about 18,000 years ago, what was dry land. And there's been archaeological evidence of not only human civilizations in these areas, but also entire ecosystems. And the significance of these is that they probably allowed the migration of organisms from, areas that we don't think of as connected today. So this is Northern Europe. And this is the United Kingdom and Ireland. Now, the United Kingdom and Ireland are isolated islands, but 16 to 18,000 years ago, they were physically connected to mainland Europe by this area that's now called Doggerland, based on kind of some archaeological evidence. I'm not 100% sure where the name came from, though I think it's kind of cute. It's like, hey, Dogland. Anyway, so those were areas that used to be settled not only by humans, but there were entire flourishing ecosystems there. This can explain how some species may have gotten from Northern Europe to the United Kingdom. They wouldn't have had to swim across the English Channel. And then Beringia is thought to have allowed migration from Eurasia over to the Americas. So when you have these major environmental changes, that can change habitats as well. So here's a big example. About 7 to 12,000 years ago, there was a change in the monsoon pattern of Africa. So there is this area in south of the Sahara that has these seasonal monsoons that come in that give a lot of precipitation and allow those areas to be fertile and support grasslands and human settlement. Well, around 7 to 12,000 years ago, that monsoon pattern shifted north. So normally, nowadays it's down here. it shifted north and ended up increasing precipitation in the modern day Sahara region dramatically. This is called the African humid period, and there is archaeological and paleontological evidence that humans settled in this area, which was more like a grassland, and that there were different animal populations there. For example, the area that's currently the Sahara used to boast giraffes, hippos, elephants, some of the animals that we now think of as belonging in sub-Saharan Africa. Then around 5,000 years ago, this pattern changed back, and that's kind of the modern conditions that we're in. Then this area received less precipitation, and then it became desertified and it turned into desert. And it's the pretty uninhabitable region that we have today. I say pretty uninhabitable because there's not a lot of vegetation there. When you have too dramatic a change in the climate, that can cause species to go extinct. And if you have a much higher than normal rate of species extinction, we define that as a mass extinction. So here we have a diagram showing us the 5 major mass extinctions that have occurred throughout history. So there's the end Ordovician, where about 86% of all the species on the planet went extinct. Then there's the late Devonian, around 360 million years ago. About 75% of all the species that existed went extinct. The end Permian was a pretty dramatic one. 96% of species went extinct. This is thought to be kind of one of the closest we've ever come on this planet to all life dying out. Then you have things like the end Triassic, and you have the end Cretaceous. This is the one 65 million years ago that led to the extinction of the non-bird dinosaurs. So all of these tend to be linked with some sort of change in climate and physical circumstances. So for example, the end Ordovician, where about 85% of organisms died off 450 million years ago, is thought to have resulted from rapid global cooling, which resulted in sea levels falling, and that would have an impact on, for example, marine organisms that used to live in shallow coastal areas that would then end up being exposed to the air and dying out. Then you have the Devonian around 340 million years ago. There was likely some asteroid impacts that led to rapid global cooling because remember, when asteroids strike, it puts a lot of dust and debris into the air, which can end up absorbing or reflecting sunlight. The end Permian was likely caused by a bunch of volcanic activity that just happened in a very short period of time. That increased greenhouse gases in the atmosphere. It put a lot of methane and CO2 into the air. There are also some thoughts that maybe there were some areas where volcanoes ended up igniting fossil fuels, and that can cause a bunch of CO2 to enter the air, and that ended up causing rapid climate change. In this case, probably on the order of, hundreds of thousands to a million years, but relatively rapid, and that led to a massive dying. In the Triassic, the likely cause was something made methane and CO2 levels rise, which resulted in rapid global warming. And then the end of the Cretaceous period, when that asteroid hit, that asteroid impact probably put a lot of ash and dust into the air, but there may have also been some volcanic activity that ended up cooling the planet, and like here it's called a nuclear winter. But basically, for a while, a lot of producers died, and there really wasn't a lot of food, so you ended up having widespread starvation and collapse of a lot of food chains. So, what are some of the other effects that these natural disruptions can have on organisms? Well, it can make them move or migrate. So let's look at a couple of the reasons for migration. You may think of migration and think of seasonal migration. So there are some animals that have these, they have their summer grounds and their winter grounds, and they fly or they run in between those two areas. You probably think of birds, they'll fly south in the winter and north in the summer. This is showing you the monarch butterfly migration pattern. So in the winter, they tend to all come to this one area in Mexico where they'll reproduce, and they'll overwinter there, and then they'll migrate north, and they'll be found in these wide areas of the United States. And this is a yearly migration pattern that they have. They do this because they're trying to have maximum access to resources. So in the winter months, it would not make sense to live in the far north because things may be covered in ice, the temperatures are colder, probably harsher for, butterflies to live. However, if they stayed in the north in the summer, in the winter, and if they stayed in the south, sorry, in the summer, it might get too hot for them, and it might be harder for them to find food sources. However, you can have also these long-term migrations in response to various disturbances. So if you have these long-term climate shifts like the ice ages, that can change the distribution of plants. So this diagram right here is showing you where spruce trees were living around 21,000 years ago during one of the major ice ages. They were living here and they were living here. Nowadays, with very decreased amounts of glacial cover, then you have spruce have a much wider range. So those plants were able to shift their range in response to these more gradual changes in climate. When you have something very dramatic, for example, this shows you before and after the eruption of Mount St. Helens in 1980. Mount St. Helens is located in Washington State, and when it erupted, it was not expected. It was one of those episodic processes, and it was very difficult to predict, and it really was a huge surprise. And so what you see is before and after these pictures, this eruption blew off the top of the mountain. It had massive ecological impacts, killed a lot of organisms, and in fact, a lot of these larger mammals, they just died in the area. They got killed by the volcanic eruption. So for example, local elk populations decreased dramatically because they died off. However, once plants started regrowing in the area, you had elk migrating in from neighboring areas to repopulate the area. So that's an example of kind of a more short-term migration in response to a natural disturbance. So that is it. We will next have a lesson put up on adaptations, which will help us figure out how organisms actually change in response to all of these different disturbances.